HER and OER, so a hydrogen evolution reaction and oxygen evolution reaction. The presentation will be focusing on the hydrogen evolution reaction. We're going to talk on why hydrogen. Everyone, hydrogen seems now to be a very hot topic, very exotic topic, but why? And how is hydrogen produced? And then we'll go into some electrocatalytic materials. We're going to explore some new electrocatalytic materials through literature review and also through some of the work that we have done. So the 4 beauties of life, as I call them, 4 beautiful elements that are important for us as humans and, as I said earlier on, for the Earth. So the first one is carbon, hydrogen, oxygen, and nitrogen. This is something that is not just have been important over the last 100, 200 years. This has been important since the Romans, Greeks, etc. So those type of materials, they have been important to all of us, especially in terms of combination of those particular elements, and have produced different molecules that have been also interesting for us, like for example, water, air, hydrocarbons, etc. So as we can see them in every aspect of everyday life. So first of all, I'm going to start to what is electrochemistry? Why it's important? So electrochemistry, as I put in there a couple of definitions, is a study of chemical processes that causes electrons to move. So some electrons will go from one side to the other, and the reason is why. And the reason is depend on the redox reactions. This is a reduction oxidation processes. So what we have, the first thing is an electrochemical cell. What's in an electrochemical cell? We will have there usually 2 or 3 electrodes. In this particular case, we have 2 electrodes, an anode and a cathode. And then we will have 2 particular half reactions. And this is where I was explaining earlier on before about hydrogen evolution reaction and oxygen evolution reaction. So we have 2 half reactions every time we have an electrochemical cell. In this particular case, an electrochemical cell, also what we have is important. We have electrodes, solution, electrolytes, and some type of instrument to apply a particular current into the system. Can be a potentiostat, amperometer, or a voltmeter. In this particular case, what we have is just the reaction of water. Okay, but I will speak to you, to all of you, a little bit about that later on. So electrocatalysis, what it is? So electrocatalyst is just a catalyst that is going to increase the rate of the oxidation and reduction reactions in an electrochemical cell. So it's going to be a type of material. We're going to be looking at what are the characteristics of that particular material that is going to help us to increase that particular rate in the oxidation reduction. So some of the factors that are going to affect an electrocatalytic material is going to be, for example, the nature of the electrocatalytic particles. So what type of materials, size, shape, and surface structure. We're going to be looking at during this presentation what type of materials and the size. And we will see that depending on the materials, we'll be able to obtain a better electrocatalyst than others. We're also going to look at the nature of the support, so material, surface structure, and electron transfer properties, and also the interaction between the catalytic particles and the support material. 3 main properties of electrocatalysts are activity, stability, and selectivity. So we're going to talk a bit about that. So when we talk about activity, we talk about the current density. Okay, so it's how it's generating and how fast a reaction is taking place. And we're going to give a particular applied potential. That relationship between the rate of the electrochemical reaction and the over potential is called the Tafel equation. I'm not going to go into equations or anything like that. I just wanted to mention because this is important when we designed electrocatalyst materials. So now we're going to go into another concept, which is important, which is the electrolysis of water. So electrolysis is coming from two particular words there, electro and lysis. Lysis is coming from Greek, so it means breaking or loosening. So in this particular case, what it means is the water in this particular case is splitting into oxygen and hydrogen, which this is fantastic. So hydrogen can be used, as I put there, as a hydrogen fuel, and or remix again with oxygen to create another type of gas called oxyhydrogen gas, which is used in other applications such as welding. Electrolysis of water, I want actually to show you with my glass of water and my two type of electrodes that I have today, but the battery that I had is in the car and it went to the MOT yesterday. Unfortunately, failed the MOT. So I had a battery inside with a torch and I was not able to show you properly. But anyway, what we're trying to do is put two particular electrodes into a system of water and with some, let's say it, salt. The salt is an electrolyte to help the ions to move faster. And then we will apply a particular current, okay, to form the oxygen and hydrogen, as I put in there. So this is, unfortunately, this morning I was looking for a particular picture to show that. So here we have two electrodes. One of the oldest electrodes that we have there is a pencil. A pencil is mainly formed of graphite. So there what we have is two pencils and a voltage battery of 9 volts. And what we can see is just what I was mentioning earlier on. So we're seeing the formation of hydrogen bubbling by the water and splitting. Okay. So as I said, when the water splits, there are two types of reactions. One is called the oxygen evolution reaction, OER, and the other one is called the hydrogen evolution reaction, HER. From now on, we will just mention HER. Okay. So the oxygen evolution reaction, as I mentioned earlier on, we have every time we have an electrolytic cell. So in this particular cell that we have two pencils and the voltage, we have two reactions there. One for the evolution or reaction of oxygen. So water, it creates oxygen plus protons and some electrons. So this is what we call the half reaction. That particular reaction is a little bit more complex compared to the other analog, which is the hydrogen evolution reaction. That particular reaction, the oxygen evolution reaction, appears on the anode, which mainly happens the oxidation. The other one is called the hydrogen evolution reaction. So as we mentioned earlier on, is the production of hydrogen through the process of water electrolysis. So that particular reaction is limited and based on the dissolving of molecules coming from the cathode surface. Okay, so slowly we're getting there. So the hydrogen evolution reaction, we have two protons plus two electrons, and then the formation of hydrogen. So it's the cathodic reaction, which means in the reduction section of the half cell of that particular electrolytic cell with the water electrolysis. In this particular, I just show you just two pencil electrodes, a little bit of water with salt, an electrolyte, but something that it will help us to move the reaction faster will be a catalyst. Okay. A catalyst will be important to minimize the overpotentiation to necessarily drive the hydrogen evolution reaction. So some important characteristics when we're coming to HER. So we need to have an optimal hydrogen absorption energy and also hydrogen absorption desorption behaviors, the catalysts. So those are important, especially to develop the active HER catalyst. So we have developed more space into the surface, and then we will be able to create better catalysts and better reactions. So where can we find hydrogen? Hydrogen is quite an interesting material or gas. So everyone, if someone said to you, where can you find hydrogen? You will say, God, it's everywhere. Well, yes and no. As we can see, it is everywhere, but usually it comes with other materials, like for example, methane or ammonia or other compounds. But as a gas, it's a very scarce gas. As I put in there in volt, it's less than 1%, 1 part per million per volume. By volume, so which is quite interesting. Okay, so that's the reason why we need to try to form or produce hydrogen. So I put in there are certain aspects. We can have production of hydrogen. So we have come from solar. I'm mentioning there solar power, wind power, water power, and also mention there a fuel cell. So this is the first time I mentioned that in the other concept, a fuel cell. Okay. So this is a very interesting article, 221, Dyer et al. From International Journal of Hydrogen, mentioning the hydrogen production and mentioning the advantages, disadvantages, production, and also the cost per kilowatt, as you can see. So one of the things at the moment that is the most important, or one of the main aspects, is the steam reforming of methane. Okay, so this is a particular process that is widely used to produce hydrogen. So it's a conventional technology and developed infrastructure. Percentage very high, 74 to 85, and the price is also excellent, 2.27. We can see all the processes. We can see nuclear, solar, wind, biomass, etc. But the percentages usually they are lower than the steam reforming. The other one, which is very interesting, is the one we are focusing today, which is the water electrolysis. So some interesting aspect, advantages, as I mentioned, as I highlighted there in bold, is no carbon footprint. So this is actually something very interesting. The storage and shipping problem and applicable for specific purposes. So this is something quite the disadvantages of the water electrolysis, but as we can see, the 60 and 80% efficiency, which is quite high. The other disadvantage also is the price, at the moment 10.3. We will talk about why the price is so high later on. So some of the hydrogen basics. So one of the things is the universe's most common and simplest element. So that is interesting, consisting of one proton and one electron. And as I mentioned, can be produced from fossil fuel-based feedstock. Can be produced to form electricity, nuclear, solar, etc., and can store energy. That is also very interesting. So this is another amazing property of hydrogen. As I mentioned earlier on, one of the storage properties is as it can go with, for example, methane. So it's stored in methane, okay, or for example, ammonia. So hydrogen is something that is everywhere now. So we have hydrogen buses in Aberdeen. So this is a picture, not that great, but never mind. With the Marischal College at the back and the hydrogen buses. We have the hydrogen project in Aberdeen. So as we can see it here, they have an aspect here of hydrogen production where they have different fuel cell stacks to produce hydrogen. Perfect. Okay. So, wow. So now the first thing is, it seems very clever. We are very clever creating energy from water. That is fantastic. So what I'm thinking is that must be, I'm guessing, that is that concept of idea. It must be in the last 10 years or 20 years. I'm guessing it must be. Well, we are wrong. A fuel cell is coming from the, as I put in there, from 19th century. So that is one of the first experiments, Sir William Robert Roth, as I put in here. And this is one of the fuel cells that Grove experiment did in 1839. So as you can see, it's nearly 200 years. And it's still, well, we're not there yet. Anyway, so here is very interesting because it's using something that we're going to talk about later on. Is put platinum electrodes. Wow, platinum electrodes. We'll see later on that I'm going to show you a graph using DFT, density functional theory, and AB initio, and other computational techniques to say the platinum is one of the best catalysts. Well, those people didn't have many computers and they knew. So here we have platinum electrodes using as a catalyst and the idea of hydrogen formation. Okay. There's another colleague also, Christian Frederick Schorbein. So again, did a similar experiment. This is more like we can see here. You can see a stack of a particular fuel cell. The first initial try. Okay. So some of the chemistry behind of the technology of a fuel cell. I have one here, so I'm going to show you in a minute. I bought it the other day. I was bored at home, so I said, okay, let me just buy something. So this is just a system of a fuel cell, as you can see. Hopefully you can see very well. So we have, that is the fuel cell. So we have two parts on the fuel cell. So we have two different sides, one and another, and one separation membrane, okay, in between both of them. So this is what it's trying to mimic, is what we said earlier on about the electrolytic cell. So two half reactions, one the oxidation and another reduction. Okay. So as I said, this is a beautiful system. And so that is my toy to play when I board here. Okay. So I'm going to put it here back at the window. So as I said, we have the oxidation and reduction system in here. So we have half and half of the reaction. Perfect. So something interesting. We have said so far that hydrogen produced can be produced different sources. And one of the interesting aspects that I mentioned here, coming from the UK Energy, 2021, is in the UK, 85% of homes and 40% of the country electricity currently rely on gas. In the US, 47% rely on natural gas. Okay. So what is a natural gas? So natural gas is mainly formed by methane. Okay. So this is a natural gas. It is interesting because this is a cleaner alternative to coal. Coal has been one of the dirtiest alternative that it has been used and forming heating our houses and electricity, etc. But now it's a cleaner one, methane, natural gas. However, what happened to natural gas? When it's burnt, what happened? It provides heat, yes, but also one of our friends, CO2. Okay, that at the moment is categorized into the bad guys. Okay, CO2. Okay, so far, what we know so far, so we know about electrodes, electrolysis of water, some electrocatalysts, and also some hydrogen evolution reaction. So we're going to go a little bit deeper. So which one are the best electrocatalysts? Well, depending on by this graph, one of the important things is should possess, we said, an ideal hydrogen evolution reaction catalyst. Electrocatalyst should possess hydrogen absorption energies approaching zero. Okay, so as I said, this is coming from experimental as well as DFT, dimensional functional theory, and ab initio programming to calculate the particular values. So we have platinum, we have palladium, we have rhenium, iridium, nickel, wolframium, different metals in here. Okay. And one of the things we said is approaching zero. So the one approaches zero is platinum. Okay. So platinum is, that's the reason why Grove and Robin, they used platinum when they were designing fuel cells in the 19th century. Okay, so it's the best electrocatalyst at the moment. Okay. However, the electrocatalyst platinum has some advantages and some disadvantages. So it's very effective for splitting water, okay, and producing therefore hydrogen. However, as our friend will say from ABBA, money, money, money must be funny in a rich man world. So very high cost. Okay, you can see, as you can see by my singing, why I'm dedicating my life to other things, no singing. So the cost of platinum is high. So therefore, that's why when I show you the table with the cost, what the cost was higher compared to, for example, reforming and creating production of hydrogen. Okay. The active sites are only located on the surface of the catalyst particles. So what can we do to increase that? So to increase that, what we can do is create nanoparticles. So this is something actually quite interesting that we have developed as a society in the 21st century, which are nanoparticles. And this is something that we have an advantage against the 19th century fuel cells. So that is something that obviously has helped a lot. So downsizing the catalyst nanoparticle to single atoms is highly desirable, as I put in there, to maximize their efficiency, okay? Because we are going to use nearly all the platinum atoms. So by using that and creating nanoparticles, we're going to create a better electrocatalyst. The other thing, just to try to save a little bit of money, is to reduce the loading amount of platinum metal by adding materials such as carbon, okay? Carbon, nitrogen, as we are going to see in a minute. Compounds as a support material. The good thing about carbon materials, as we're going to talk in a minute, is they can be precisely controlled. So they can be, in the nanostructure, they can be looking at a high specific surface area. So this is what we are interested in. Absorption, desorption. Okay, so it's a high specific surface area. Any more advantages? Yes, we have the substrate enhanced electrical conductivity, allowing fast electron transfer, okay, in the hydrogen evolution reaction. And also a superior catalytic activity can be induced by strong interaction and synergistic effect of the metallic species and the carbon support. We will look at in examples in a minute what I'm saying. So the first example, we're going now a little bit deeper into some of the literature review and some of the hot topics and hot electrocatalyst, and one of them is using this particular system. So using a platinum single atom and cluster catalyst through the hydrogen evolution reaction. So in this particular system, some of you will be familiar to that particular figure on the left hand side, which is graphene. Okay, so our friend graphene, which is obviously now another hot material, has been very has attracted a lot of attention, and many of us we have been trying to use it in different applications, sometimes working, sometimes not working, but never mind, this is a different story. So there we have graphene there, and what we have also in this particular system, what they have used is nitrogen atom. So the nitrogen atom, as you can see, are the green ones introduced into the system. So what they call a nitrogen dopant. Okay, so a dopant, it means that we introduce nitrogen into a particular system. That's what we do, what we did, the particular group, Cheng et al. This is published in Nature Communication 2016, where they introduce is a platinum precursor, and then forming the single atom cluster, okay, which is obviously here on the right hand side, okay, through a particular reaction with oxygen exposure. So, as I said, they use a nitrogen doped with graphene nanosheet, okay, matrix. How they introduced that particular system? They use an atomic layer deposition, which is a method to deposit particular material into a system. Okay. So they compare in this, as I put in this figure, the mass activity of different catalysts. So you can buy as a platinum catalyst and then compare it with that. So they have used the ALD, as I said, atomic layer deposition, and platinum nano nitrogen dope graphene nanosheets, and then 50 and 100 are the number of cycles they have used. Okay, so they seem that 50 cycles they gave us the best results. Okay, so this is obviously quite encouraging, especially for the hydrogen evolution reaction as we are talking about. Okay, some of the disadvantages we can see is obviously there is some experimental work and there are some introduction of techniques, atomic layer deposition and nitrogen dope graphene nanosheet, etc. So those materials, they can be difficult to maneuver, so we can say, and then also the price can be also high. But in terms of the capacity, this is quite interesting as electrocatalyst. The other one that we're going to be looking at is again with platinum. But again, as we said earlier on, we said that downsizing is very important. It's a key thing. So again, here there is another system using a nanowire. Okay, so a particular platinum downsizing the platinum in order to increase the absorption-desorption active sites. So here there is a single atom tailoring of platinum nanocatalyst for the hydrogen performance multifractional electrocatalysis. So they use what they call here a SANI, so a single atom nickel. So they are another type of metal, species on ultrafine platinum nanowires. So they have used that particular system. And the reason, as I said earlier on, so they use a platinum nanowires to downsize the system, and they use also a nickel in order to create a synergetic effect between the two metals. So it's called a bimetallic approach. Okay. This is quite interesting. So I wanted to show that because I work on cyclic voltammetry and voltammetry, etc. So I want to just get excited and talk a little bit of that. So when they created that system, they didn't know if they were able to introduce nickel into the system. So what they did was using a particular system called a cyclic voltammetry, yet to look at if the oxidation reduction of that nickel was actually there. So they compare the pure platinum nanowires with the platinum nanowires with nickel. Okay, so we can see the system redox nickel 2 to nickel 3 plus around 1.32 and 1.34 volts around that area, right hand side here. And then this is the oxidation reduction system. So it seems that nickel 2 and nickel 3, they were indeed introduced into the system. So the single atom nickel was introduced into that particular system. Again, another interesting article, this is 2009, as I mentioned there. And the other one we're going to be looking at, this is another metal, which is very interesting. It's completely different. So before we were looking at platinum, still the base of platinum, and now we're going to move a little bit to other materials. So in this particular case, another metal using ruthenium. Ruthenium is very interesting material, especially as I've mentioned it there, because it's an expensive alternative to platinum. Okay, so it has a similar metal hydrogen bond strength and enables ruthenium to exhibit some interesting and comparable hydrogen evolution reaction activity compared to platinum. So that is very interesting. I put a picture of ruthenium here. That is the metal ruthenium. And in this particular case, what they have done, they use ruthenium again into another structure. Okay, so a two-dimensional carbon nitrogen structure. Okay, to form that particular catalyst. As we mentioned earlier on, one of the beauties of carbon or nitrogen materials is just they can be downsized and also they increase the surface area. Okay, so that's the reason why they use usually a particular metal with carbon-based compounds. So this is what it looked like. So they have, as I said, the carbon nitrogen systems in layers, and then the ruthenium in between each layer. Okay, and producing that electrocatalytic system for the production of hydrogen. Another interesting paper from Nature Nanotechnology. So now we're moving into another one that was again quite interesting. In this particular case, they use another type of metal, iridium. Okay, and then we have another, as I mentioned earlier on, a bimetallic synergistic effect with tungsten. Okay, and again they use a system of, in this particular case, nanodendrites. Okay, so this is another type of material, again into downsizing, what I mentioned earlier on as a property to create a particular system that I put in here. Okay, that was very interesting. They tried the hydrogen evolution reaction in both media, acid and alkaline, and it worked really well. So that was again another interesting article from the ACS, American Chemical Society. The other one, other interesting article coming from Advanced Material Interface. So in this particular case, they have used platinum and copper alloy nanoparticles as again that bimetallic system, and again using that type of nanoparticle or into carbon nanofibers. Okay, so again downsizing, as I mentioned earlier on, and this is something that we replaced, where they replaced the noble metal content with a low cost earth abundant non-noble metal. Okay, so in this particular case they use it, for instance, copper. Some of the noble materials, so as I mentioned earlier on, platinum, this is one of the noble materials, and copper in this particular case is non-noble material. So how they introduce that particular system? So they use different techniques. So one is electrospinning and graphitization to encapsulate the platinum copper nanoparticles into carbon nanofiber. So as I mentioned earlier on, there is an excellent performance as a catalyst, and this is attributed, as I mentioned, to the bimetallic effect between the platinum and copper. Okay. So they mention also the uniform distribution of the alloys, nanoparticles, and the use of carbon nanofibers with 3D architecture. We have been missing our friend graphene. So here we are with graphene again. So in this particular case, they use cobalt and also a type of nanomaterial, which is nanorods. Okay, so they have used graphene oxide. They used tetraethylene orthosilicates and different calcination, precursor, and phosphorylation to and hydrogen fluoride for etching to create that particular system, which, as you can see, it has many active sites which work really well as an electrocatalyst. And again, this is the electrocatalyst can be attributed to the mesoporous structure, as I mentioned earlier on, and the synergistic effect between the copper and the cobalt and iron and the phosphorus. So this is something, as I said, another interesting aspect. The other one, what we're going to mention today, is just with other type of material, but again, with graphene oxide template, and this is with thallium and nitrogen system, nanometers again. Okay, so again, we go into the nano size aspect. As I said, this is a special property into the catalyst to create a beta catalyst, which is going to the nano size. So they use a hydrolysis process and calcination step to form a two-dimensional tantalum oxide layer, which one they converted into the final nitridization step, okay, to form that particular compound there. So a highly crystalline structure of that particular system. And as we can see here, this is what they have done over the process. Okay, so the graphene oxide with the thallium chloride as a precursor, and then hydrolysis and calcination to form final system in this particular case. So nano meshes again, as I said earlier on, very interesting type of active sites, especially to work as an electrocatalyst. The other one I wanted to mention is another aspect, so a molybdenum with selenium. They have mentioned here, that's what I mentioned earlier on, a TAFL, slopes, to look at the electrocatalyst, and then have used this particular material. One of the problems it has is kind of expensive. Okay, so they have used hydrostructure again with either graphene or other carbon nanotube, just to make it, as I said, and go into the downsize part of the system and increase the active sites. So this is how the system appears. So different processes into the, for example, here the graphene, and you can see aniline in hydrogen to form a particular system, or lithium intercalation to form the other system here. Okay, and this is, we're moving now to something that we have done in here. So as you can see, we have used, in this particular case, we have used a particular material, the tungsten, and also molybdenum oxide nanowires and reduced graphene oxide nanocomposite. Okay, so first of all, this is, as I mentioned earlier on, so go into the downsize. and looking at the bimetallic effect of two materials, two metals, like a tungsten and molybdenum. So this is create a high electrocatalytic effect, and it's important for the hydrogen evolution reaction, as I mentioned here. So a synergistic effect, as we mentioned earlier on. Okay. The other one, quite interesting, is just again another type of nanocube materials by again palladium and lead. Okay, so in this particular case, created those nanocubes, as I mentioned, as I put in there, and those particular nanocubes, they work really well as electrocatalyst for hydrogen evolution reaction and other applications that we also be looking at. So we use the palladium 2 acetonate, olelylamine, and lead acetate, and this we created, as I put in those pictures, nanocubes with a large surface area. The key parameter here was the introduction of CTAP, so as cetyl 3-methyl ammonium bromide. Okay, so this was very important in the reaction, which obviously helps to create those particular nanocubes. The other one we have also worked is platinum silver nanodendrite. So this is again another interesting bimetallic system that increased the electrocatalytic effect of when it was applied for the hydrogen evolution reaction. Okay. And also another one have you introduced is a molecular fluorinate phthalocyanide immobilized into a mesoporous carbon. Okay, so the mesoporous carbons created very interactive bifunctional electrocatalytic effect and through the hydrogen evolution reaction. So here we construct that particular or the mesoporous carbon through the molecular cobalt electrocatalyst via the PP stacking methods. Okay, catalytic effect for the hydrogen evolution reaction as well as other systems. So some of the conclusions, as you can see, there are alternatives. We have looked at that to platinum by combining other metals. We have seen, for example, palladium. We have seen iridium, ruthenium with carbon or nitrogen-based compounds. We have seen looking at mesoporous carbons. We have been looking at graphene. We can look at graphene oxide, reduced graphene oxide. So that particular combinations has made a better electrocatalyst. We have also spoke about carbon and nitrogen-based compounds, which have shown a versatile platform for the absorption, nucleation, and growth of metal nanoparticles. This is important, and also it has provided abundant coordination sites for the distribution of small size metal nanoparticles with the carbon-nitrogen-based compound layers. So also we said the excellent hydrogen evolution reaction performance of B metals attributed to the synergistic interaction between the both metals. So those are the conclusions from today. And my last slide is going to barriers to implementation. So are we there yet with hydrogen? So in general market, we see viewed as a long term, maybe 20, 30 years still. Hydrogen usage viewed with trepidation by public. So there is a lot to do. Current hydrogen production costs, as I mentioned, higher than conventional, for instance, natural gas or other type of systems, like we mentioned. Technological numerous technical challenges for each of the renewable pathways. We don't have at the moment limited industry interest. Well, there are industry interest, but slowly. So this is something interesting, and the investment in research and development is also increasing. So this is something interesting, but also infrastructure is something that we are still need to be work on that. So acknowledgement, it goes into different members and system and platforms. So research committees from PALS, some of the universities in China, Ludong University, for instance, Yanshan University, Interface, ETP, School of Pharmacy, obviously National Subsea Center, at the Royal Society of Chemistry, Analytical Chemistry is fun, and also some names that over the years have helped me to develop and also help me with the research. So they are in here. So thank you so much for listening. Thank you.
Okay, thanks very much, Carlos. That's brilliant. We presume we got a few questions probably to address. So maybe start in the chat here. I think the first question is from Wilma, which are the materials currently in commercial electrolyzers? I think he's referring to graphene and MOC.
If they are electrolyzers, they are commercialized.
So they're already available.
They're already available. I don't think so. They will be available as a commercial. You can buy them a commercial, yes, but ready available for electrolyzers, I don't think so. And one of the reasons is at the moment still the cost is very high. So this is one of the downsides.
Okay, so can I follow a little bit on that?
Yes.
What do you think we will need to do to make them more readily available so that there'll be more options beyond the limited availability on the specific electrolyzers?
Yes, so this is a very interesting question. So one of the things we need to do is at the moment graphene, the way it's synthesized slowly, we're getting more ways or methods to synthesize graphene quicker and faster, quicker and cheaper. So this is something that over the years it will help to decrease the price and therefore to be able to commercialize graphene properly.
That's good. And I got another question here from Alberto. He's asking, performance of this type of electrocatalyst looks good. What about chemical and mechanical stability?
Again, very interesting question. Thank you. So some of the stability, this is obviously made in the laboratory, as I mentioned, some of the stability with the materials in terms of, for example, let's say, if they are robust enough over a period of time, can they be printed, for example, in to be used in an electrolyzer, etc. There is still some of them, for instance, they have better life than others. Okay, so when you have two metallic compounds, the life will be higher. But when you introduce other materials like graphene or graphene oxide or reduced graphene or nitrogen dope, etc., the life, in my opinion, could be shorter. So there is still to work on that. Yes.
All right. Okay. I think there are probably more questions coming through, but in the meantime, maybe I can ask one regarding very early stage of your presentation. You give an example of pencil being used for graphene for water breakdown to hydrogen and oxygen. So the question is, do you think graphite has a lot to play, particularly on high purity levels? You know, could we just use graphite instead of graphene? because graphite is cheaper, obviously, and more available?
This is a very interesting question. Indeed, graphite is the, I will call it the ugliest brother of graphene. So, but it's the more efficient. Okay, so far it's one of the best materials readily available. Graphite, yes, absolutely, absolutely.
Okay. Any reason why it's not widely used?
The reason it's not widely used is at the moment graphene offers some interesting properties compared to graphite, so the large surface area. So that quite interesting property, and some of the electrical conductivity, which is also interesting. Okay.
Okay, good. We got another question here from Wilma. With the focus of design, with the end of life in mind, how recyclable would graphene be? I think referring to most of the byproducts or chemical you've featured, that some of them will have graphene element on them. So how recyclable are they?
Okay, this is very interesting. How recyclable? I'm not quite sure, but I'm guessing it would be a possibility to recycle them. Yes, but I'm not very sure.
All right, but my perception is that graphene is purely carbon and oxygen.
Yes.
Chain links depending on depending on the structure and the level of purity that you have in graphene. So perhaps you should break that down back to carbon if you do want to.
Yes, exactly. It will depend obviously in the purity. Yes, absolutely.
Right,
sometimes the graphene that it created is not the graphene absolutely pure. This is where the problems are encountered. Yes, absolutely.
Right. Okay. I may have another question in the meantime. Maybe unless if someone got a question, please ask. It's a good chance to ask all the difficult questions to the right person. It's around oxygen. Obviously, we're producing all these hydrogen, and if you're producing tons of hydrogen, we'll be producing tons of oxygen on the other end of it. What do you think we should be doing with that?
It's very interesting, exactly. So when the water electrolysis, as I mentioned earlier on, it created into an electrolytic cell. So in that particular cell, you will have two half reactions, one producing hydrogen, as you well said, and the other producing oxygen. Absolutely. High oxygen at the moment is used to work on oxyhydrogen gas, as I mentioned, in welding, other type of materials. However, oxygen can also be used as an oxidant. So this is something interesting to be used, for example, a level of oxidation of different materials. Yes.
Yeah, that's great. And I can ask also another one, just because of a bit of time. In terms of the cost and availability, we're talking about critical raw material, particularly on the metal side of it. From your point of view, do you think there's a chance to replace some of those higher critical raw materials? The metal group that you're working with, the palladium and all that, they are very expensive, rarely available, difficult to find, and so on. Any replacement suggestions in the future, do you think?
This is again another very interesting question. I think one of the things that need to be explored further is just to use more recyclable materials, more sustainable materials. At the moment, those materials expensive, yes, but they could be recycled. They could be recycled. That would be the key thing. And then to avoid the cost, to have a particular system where you don't just waste the platinum, that you can reuse the platinum several times.
Oh, brilliant. I think, Carlos, thanks very much for answering our questions, and also for a very good presentation, very interactive, and covering all the critical issues. I think we've got one more question here. I was just about you off, but Matthew is asking, with the increase in the reactive surface of metals using the tubes, I believe. How do you ensure you have materials lasting longer to produce hydrogen?
So that is very interesting. So thank you, Matthew. So the idea will be to, as you mentioned, with that large surface area, you will reduce the cost of platinum or other metals, because the idea is to increase that particular large surface area. But we need to have, and that is the key thing, we need to have a compromise. Because if we add, let's say, this is like a recipe with food. If we add, let's say, more carbon than platinum, the reaction, it won't work. Okay, so we need to have the right amount of platinum or a catalyst with a carbon-based material or nitrogen-based materials.
Well, thanks very much for that response, and many thanks for the audience and participants. We really appreciate that. There will be another series event which will follow through in not long from now. Please do join us in I think in the beginning of September. And most of all, thanks for Gemma Reynolds for organizing this event, and also for all the other team behind the scene who have helped to put together the event. My sincere thanks and to Carlos for availing yourselves and a very good interactive presentation for this particular topic, and also to, strengthening the topic and widening up the issues around the electrolysis processes in building up of the electrolyzers and other hydrogen production systems. Okay, and that's for us. Thanks very much for the time.
Thank you so much. Thank you, James, and everyone for coming. And Gemma,
Nice weekend.
Bye bye. Have a nice weekend.
Bye.